Alright, in this video we're going to look at multi-step integration by parts, which basically is like the simple integration by parts we've talked about before, except instead of only having a single application of integration by parts, we're going to have multiple ones, where we'll do integration by parts, and it'll leave us with an integral where we need to apply integration by parts again. And we'll see what's going on with that in this one. Alright, first of all, I'm going to decide my first u and my first v. Looking at this, I've got a polynomial and an exponential. Polynomials come first in my hierarchy, so I'm going to let u be equal to x squared, and dv be equal to e to the x dx. Find my v. Find my du. Wow. And then I find my v. Sometimes the brain gets a little bit ahead of itself. And now this is going to be equal to u times v minus the integral of v du. And now I have an integral in this one where 2x e to the x is something that I'm also going to need to integrate using integration by parts. And so in this case now I'm going to let u be equal to 2x and dv be equal to e to the x dx. If it helps you, you can subscript the u's and dv's and stuff. I typically don't. I typically just continually recycle those letters u and dv when I'm doing multi-step integration by parts. So now, du is going to be equal to 2dx, and v is going to be equal to e to the x. And so now this turns into x squared e to the x minus, and I want to make sure that I subtract the whole quantity that I apply when I get this into the second integration by parts. So now I'm going to have u times v minus the integral of v du and I'm just going to go ahead and distribute that subtraction sign a while. And now I have an integral that I can find without using parts, just by using direct anti-differentiation. And so I'm going to do that. And the integral of 2e to the x is 2e to the x. Get your constant. And there's my final answer there. If you want to, you could factor out an e to the x here and write that as e to the x times quantity x squared minus 2x plus 2. Either one of these I find acceptable. Alright, so basically when we do multi-step integration by parts, all we're doing is applying it once, and then once we're done applying it once, applying it again. Alright, let's look at example 2. I'm going to find the integral of x to the third sine of x. We have a polynomial and a trigonometric, so the polynomial is higher in our LIPAT hierarchy. So we're going to do u equals x cubed, and dv equals sine of x dx. And du is 3x squared dx, and v is, let's see, integral of sine of x is negative cosine of x. So this is going to be uv, negative x cubed cosine of x, minus the integral of v du. And since I'm taking minus an integral of negative 3x squared cosine of x, I'm going to shift that over and just pull that negative sign out and change our subtraction to an addition. And now I'm going to apply parts again. So we've got u equals 3x squared, dv equals cosine of x dx. And then du is 6x, and v is sine of x. Oops, not dx, I know. 6x. There we go. And so now this becomes negative x cubed cosine of x plus, alright, let's see, uv is 3x squared sine of x minus the integral of v du, integral of 6x sine of x dx. And now we need to apply parts one more time here, a third time in this problem. So u is equal to 6x, v is equal to sine of x dx, and so du is 6 dx, v is negative cosine of x, and so I've got negative x cubed cosine of x plus 3x squared sine of x minus uv minus the integral of v du minus the integral of the negative. So again, I'm going to pull that negative sign out in front of the integral there. And I guess I'll distribute my negative sign. And now I have an integral here that I can take by anti-differentiation. It's just going to be 6 sine of x. So there's the integral of x to the third sine of x dx. Alright, that's the end of this video. See you next time.